So now we move on to reactions of alcohols. And by far, the most important reaction that we have for alcohols is the oxidation. The oxidation reaction of an alcohol allows us to convert an alcohol into a carbonyl. And we control what kind of carbonyl we form based on the type of alcohol that we start with. So it makes a big difference whether we start this reaction with a primary, secondary, or tertiary alcohol. So if we start with a primary alcohol first gets converted to the aldehyde, and then depending on the reagent we use, and we'll talk about examples of both later on, sometimes that reaction will stop at the aldehyde, and sometimes it'll continue on, and we form a carboxylic acid as the product. When we start with a secondary alcohol, secondary alcohols get oxidized to form ketones. And what about tertiary alcohols? Well, the issue in these reactions is what's getting removed is the hydrogen that's on the alcohol and then a hydrogen that's on that adjacent carbon. If we have a tertiary alcohol, tertiary alcohols have no hydrogen at that point. And since they have no hydrogen at that point, they can't be oxidized. So these oxidation reactions are generally limited to the use of primary and secondary alcohols. And these reactions are most commonly done, although there's a lot of different ways to do them, but they're most commonly done with highly oxidized metals. And in this class, we're going to see several examples here, starting with highly oxidized chromium metal. But manganese is also very commonly used, as are others. So the first specific example that we'll look at uses what's known as Jones reagent. Jones reagent is formed by making a mixture of chromium trioxide and sulfuric acid, and then we get what ends up being our active reagent, this species. And if we calculate the oxidation number here, we can see that we're starting with chromium 6. So how does this reaction work? So we'll start in this first example with a secondary alcohol. And so under these conditions, the alcohol is able to remove a proton from the chromium species, taking us here. Now, you may recall from some of our previous chapters as to one of the most common reasons that we protonate alcohols in reactions like this. And the reason is that we need to make the alcohol, we want to get rid of it. So we need to make it into a better leaving group. And so by protonating the alcohol, that's exactly what we've done. And you may recall that we saw this in elimination reactions. When we wanted to eliminate an alcohol to form an alkene or a dehydration reaction, we did exactly the same thing. We protonated it to make it into a good leaving group. And so from here, this O minus adds in and kicks out water. So we've now replaced that entire chromium group, or I'm sorry, the OH group, with this chromium species. And so from here, if we have something basic, and we don't need something strongly basic, water is good enough. Lone pair on oxygen can grab this proton, these electrons shift up, and we kick out the chromium group. So we've done, at least in this step, what looks very much like an elimination reaction. And this is also why we needed the chromium on there, because if we tried to do that over here with the alcohol, that H minus, of course, is a terrible leaving group. But by replacing it with this chromium piece, we've made it into a much better leaving group. And so we form our product, carbonyl, plus our chromium byproduct. And so if you compare what we started with, we can see both the oxidation when it comes to carbon, and we can see the resulting reduction with chromium. So chromium, we previously said, started as chromium 6. In the product, though, we have chromium 4. And so we can see now that the chromium has gained 2 electrons, or it's been reduced. And let's correct our arrow. Everything we've said is correct, we just have the arrow going in the wrong direction. What about the carbon? So the carbon started with an oxidation number of 0 and ended with an oxidation number of +2. So carbon lost 2 electrons, or it was oxidized. And so remember, even though we talk about this reaction as an oxidation, we talk about it that way because the oxidation is what's happening to carbon. Something else still has to be gaining electrons, and we can see in this case that that's the chromium. Now, this reaction isn't necessarily done, though. Under strongly acidic conditions, and if you noticed on the previous slide, we've got sulfuric acid here, so these conditions would certainly qualify. Carbonyl is in equilibrium with a species known as a hydrate. Now, for most carbonyls, we don't really worry about this step. This is an equilibrium that in almost every case strongly favors the carbonyl. And when I say strongly favors, for your typical carbonyl, it's well over 99.99% is favoring the carbonyl. And so in this situation where we're dealing with a ketone, it forms the hydrate, but there's nowhere for the hydrate to go. But what happens if we have a primary alcohol? So I'm not going to walk through the mechanism here because it's the exact same mechanism that we just did for the secondary alcohol. But a primary alcohol gets oxidized to the aldehyde. We then have, again, this very strong equilibrium that favors the carbonyl, but does exist to give us the hydrate. But the difference here, and this is the key difference, The hydrate of an aldehyde still has this hydrogen here. And so if you form any of the hydrate, even 1/1000th of 1%, because you have another hydrogen there which doesn't exist in the ketone, this can be oxidized a second time. Exact same mechanism, but it gives you the carboxylic acid. Now you might ask, why is this relevant? Because we said only a tiny percentage of that aldehyde is actually going to form the hydrate. But if we think back to what we've learned about equilibrium, when we talk about equilibrium, any small amount of this hydrate that gets formed is going to get oxidized to the carboxylic acid. So any of the hydrate that gets formed actually gets taken out of the equilibrium. Well, by Le Chatelier's principle, we know that if we remove some of the product, the result is the equilibrium will shift to make up for that. And so we form more of the product. Again, very, very small amount. But because of how Le Chatelier's principle works, it doesn't matter that it's a tiny amount. The fact that it happens at all is enough to push a little bit forward. It gets oxidized, and over time, the majority of the aldehyde can be oxidized to give us the carboxylic acid. So with a primary alcohol, under the Jones reagent conditions, we form a carboxylic acid. Again, with the secondary, we get the ketone. But what if we wanted the aldehyde? And there's plenty of reasons why we might want to stop there. Well, if we want the aldehyde, then we need to use conditions that are going to not allow for this middle step. So we want to stop this hydrate formation. And so for that, we're going to need a different reagent. One of the most common ones is known as PCC, or pyridinium chlorochromate. It's also a chromium-based oxidant, but is going to behave very differently. Now, the mechanism I'm about to show you here is the same mechanism for primary or secondary alcohols. We're going to do this one with a primary alcohol, but we could just as easily do it with a secondary alcohol. So here, the alcohol attacks the chromium directly. To give us this intermediate, which then kicks out a chlorine. Also, at some point during this process, this hydrogen is lost. And again, in a species that's very, very similar to what we saw in the Jones oxidation, we've put a group onto oxygen that can function as a leaving group. Again, we don't need much of a base here at all, but anything that can function as a base can remove this hydrogen and kick out the chromium. And just like with the Jones oxidation, that gets us to the aldehyde. But in this case, the reaction's actually done. Why is the reaction done? Why doesn't it oxidize a second time to give us an acid? Well, the key difference is, and we'll learn more about how hydrates are formed later on in this course, but in order for that hydrate to form, we typically need an acid present. And the PCC conditions don't have an acid present. And so because of that, there's no hydrate formation and the reaction is done. So oxidation is by far the most important reaction for alcohols. But the other reaction I want to talk about briefly is that we can convert alcohols over to alkyl halides. And we're not going to go over the mechanism of this one here. We'll come back to this mechanism when we look at acyl substitution reactions, but I'm just going to show it so that we are aware of this reaction. So an alcohol can be treated with SOCl2 or with PBr3, and in either case will allow for replacing of the alcohol group with the halogen. A reaction like this becomes very useful, we'll see in the future, because often one of our biggest challenges in organic chemistry is forming carbon-carbon bonds. And as we'll see, carbonyls are very, very helpful for that. Well, with a reaction like this, a carbonyl can be reduced down to an alcohol, and we can convert an alcohol into an alkyl halide, and then we can do any of the things such as substitution or elimination that we've learned for alkyl halides. And so this, is sort of the introduction to, what we ultimately want to be able to do in organic chemistry, which is to synthesize complex molecules.